In this video, we will apply Bayes' theorem one more time on these medical tests. So before you begin watching the rest of the video, please read this little paragraph, pause the video and understand what it says so that we can kind of talk about these medical tests. So in these medical tests, you get two different kinds of results. False positive indicates that a person or a patient has a disease when the patient does not have the disease. So that's kind of a bad thing. And false negatives tells us again that the patient does not have the disease when the patient already has a disease. So again, that's a bad thing too. Now, in this problem that we're going to be working on, there are basically tests being given to people, and this disease is found in 5 out of 1,000 people. So 5 people will have the disease, whereas 995 will be healthy people, according to this paragraph. And in this particular scenario, we're assuming that the false positives show up at 3% and the false negatives is 1%. So vice versa, that means that 99% of the time, a person who has the condition tests positive for it, whereas 97% of the time, a patient who does not have the condition tests negative for it. So let's try to kind of summarize what we just read in a small tree or a probability tree. So I'm going to start by designing my tree as follows. So first I give the test and a person has a disease. So I'm going to write D for disease, or does not have the disease. I'm going to write not D for a person not having the disease. Now, how many people have the disease? There are 5 people in every 1,000 that have the disease. And there are 995 people out of 1,000 that do not have the disease. Now, once I give the test to somebody, then there's a possibility that the test was wrong or the test was right. So the people that have the disease, there's 2 different groups. People who will test positive and people who will test negative. So for that, I'm going to write the plus for testing positive and a negative for testing negative on the test. Now, how many people test positive and already have the disease? Let's find out by reading the paragraph again one more time. So suppose that the false positive rate is 3%. And keep in mind that false positive means what? False positive indicates that a patient has a disease when they don't really have it. So that does not apply here for us. Now, if I keep reading, the false negative rate is 1%. In other terms, false negative indicates that a patient does not have the disease when they in fact have it. So these people already have the disease, and my test is saying, no, they don't have it. So the rate here is 1%. So this is 1%, or in other terms, 0.01. So automatically, the second tree is going to be 99%. Or in other terms, 0.99. And that's what the rest of my paragraph is saying, right? So they're saying 99% of the time, a person who has a condition, meaning who has a disease already, tests positive for it. So that's great. That's the top half of the tree. And now I got to design the bottom half by reading the same paragraph again and organizing the second half. So again, a person who does not have the disease could test positive for it or could test negative. So let's find out again what the numbers are. So it says that a person tests false positive. The false positive rate is 3%. So what is false positive? False positive means that the person or the patient has a disease when the patient does not have it. So these people don't have the disease, but the test is showing that they do. So that rate is 3%. Or in other terms, 0.03. Whereas the bottom one will be 97%. Which is also 0.97. Okay, that's what my paragraph over here says. 97% of the time, a person who does not have the disease will test negative for it. So it looks like my tree is designed correctly so far. I also added some information to the tree to show us which branches were the false positive and which branch was the false negative. So if I carefully read the first branch right here, how can I interpret it? These are the people who tested positive and they have the disease. Okay, so in other terms, the probability of testing positive given that you have the disease is going to be 0.99. The second tree down here, the minus sign represents the probability who tested negative, but they already had the disease, 0.01, and so on and so forth. The next one is going to be P plus / no disease, which is 0.03. And finally, the last one is the probability of minus given not D, and that's 0.97. Now, what am I looking for in this problem? Let's take a look at the question. The question is, what's the probability that a randomly chosen person who tested positive for the disease actually has a disease? So what we're looking for in this problem is the probability of a person who tests positive for the disease actually has a disease. So disease given that they tested positive. So we already know that they test positive. What's the probability that they actually have the disease? That's what we're looking for. And that's what we're going to be trying to evaluate in this particular problem. So to help me out, and I need the space, I'm going to shrink the tree down a little bit. So the probability of P / plus is basically going to be, according to Bayes' theorem, the following. So first, I'm going to flip the plus and the D and multiply by P of D. Then I'm going to divide the problem, just like the theorem basically tells me to do. I'm going to divide the problem by the same exact thing again, plus so on and so forth, where I change the B1 to B2 to B3. So go through all the possible events in my case. And the events in my case are D or not D. So basically, I'm going to start with plus / D again. So the same thing that I wrote in the numerator times P of D plus P of plus, one more time, / not D multiplied by P not D. Okay, so why did I do this? Again, just check out what the Bayes' theorem looks like. So in the Bayes' theorem, we have the same A in front of all of the probabilities in the front, and the B in the second half pretty much goes from B1 to B2 to B3 and so on and so forth. So for me, the first letter or the first character should stay the same. So that is the plus sign that I chose, having the disease, testing positive on the test when we're checking for the disease. That should stay the same, but the second letter should change from D1 to D2 to D3 or whatever. But in my case, I called it D and not D. So having the disease and not having the disease. And now all the numbers are present in my diagram. So what is P of plus / D? That is 0.99. Multiply that by P of D, which is 5 out of 1,000. So 0.005. And that's basically this right here. P of D is the probability of having the disease, and 5 people out of each 1,000 have the disease. The probability that you don't have the disease is going to be the probability of being healthy, which is 995 divided by 1,000. I need that for the denominator. So now again, I'm going to put the same numbers one more time. That's the first part of the denominator. And then I'm going to add, so that addition sign that you're seeing right there in the middle is this addition sign. And the probability of P given not D. So that's 0.03 multiplied by the probability of not D, so being healthy basically. So multiply that by 0.995. So let's type all of this into the calculator and see what we get. So we find out that the number is, roughly speaking, 14.22%. So now let's take a look at part 2 of the problem. I would recommend that you pause the video and see if you can get it done. It's very similar to what we did above, but it's this time a minus instead of a plus. So see if you can get it done first before you watch the rest of the video. I'll give you a chance to pause it now. So as you can see, the number here turns out to be 99.99%. So there's a lot of people who will test negative for the disease and they don't have the disease basically. So that's kind of the reason why hospitals operate the way they do, and they offer these screening tests because they're very accurate. They help save money from running more expensive tests. There's a little paragraph about that in your book, actually, on page 617. I would recommend that you read it. It's pretty interesting.